Hi everyone! In this video we're going to look at some navigation problems or problems involving bearing. And specifically we're going to use definition of the true bearing. Well, let's start by defining the bearing itself. Now, while there are different ways to measure bearing, bearing itself always represents the direction of motion of an object such that a ship or airplane, or it can be direction of a second object at the distance relative to the ship or airplane. As already mentioned, in this video we're going to look into true bearing. It's just one of the ways to measure the bearing. And this is how true bearing is measured. So we measure it in clockwise direction from due north. Well, it probably doesn't make any sense yet, but as we look at the pictures, it will make perfect sense. To help us, I'm going to place the compass over here, just to remind us that the north direction is the one that goes vertically up. So let's assume that we have an airplane, and the direction of its motion, in other words, direction in which it's flying, is this one. Well, what is its bearing? As it says here, bearing is measured in clockwise direction from due north. That means that first we have to place vector that goes in the north direction. In other words, straight up. So from the north vector, we go clockwise to the direction of motion of the airplane. And let's say we were able to measure that angle, and we found that it's 40 degrees. So we're going to say that this plane flies on a bearing of 40 degrees. Let's do one more example. This time, let's say we have a ship, and here's the direction in which it's moving. How do we measure bearing? Again, we start with the vector representing the north direction, the one that goes straight up, and then we rotate clockwise until we get to the vector representing the direction of motion of that ship. Suppose that we were able to measure it accurately, and we found that this angle is 134 degrees. Well, that means that this illustrates bearing of 134 degrees, or that ship sails on a bearing of 134 degrees. And let's try this exercise in reverse. For example, we're given that the airplane is flying on a bearing of 200 degrees. In which direction is that plane flying? When we use the true bearing, we always start with vector that represents the north direction, the one that goes straight up, and from there we have to rotate 200 degrees clockwise. To help us estimate how far we need to rotate, let's set up, looks like XY plane, so it's easier for us to count angles. So if I rotate this far in the clockwise direction, I rotated 90 degrees, I have to keep going. If I rotate this far, that's going to be 180 degrees. I have to keep going just a little bit more, right? I have to rotate 20 degrees more. So I'll rotate just a little bit more and I stop. Well, that is 200 degrees rotated clockwise from the north vector. So this is basically how I rotated. 200 degrees, and that's where I stop. And now this vector here shows the direction in which plane is moving. So when we work with true bearing, we're only given a number of degrees, and automatically we know that we have to start at the north vector and rotate clockwise. Well, let's try the application problem involving true bearing. Let's read it. Radar stations A and B are on east-west line 8.6 kilometers apart. Station A detects the plane at C on a bearing of 53 degrees. Station B simultaneously detects the same plane on a bearing of 323 degrees. Find the distance from B to C. It's a lot of information, and the best way to understand what this problem is talking about is by making a labeled sketch. It's going to be crucial for this problem. And I'm also going to put a compass here to help us understand some parts of the problem. So let's start reading it again more carefully and then putting together the sketch. So it says radar stations A and B, so we're going to have 2 points A and B, are on east-west line 8.6 kilometers apart. What is east-west line? Well, here's east here's west. East-west line is just a horizontal line. Okay, like that. Station A, station B, east-west line. 8.6 kilometers apart. I'm going to add that. Next, station A detects a plane at point C, on a bearing of 53 degrees. Here's station A, and the question is, in which direction it's detecting a plane? Well, let's use what we learned about bearing. We have to start with the north vector and rotate clockwise 53 degrees. Okay, so I'm rotating 53 degrees. And where I stopped, that's where I have to place the vector showing the direction in which station A detected a plane. Do I know where exactly the plane is? No, because bearing only gives me direction. It doesn't give me the distance. That plane can be anywhere on that line. But we have another piece of information, so hopefully it will help us to find location of the plane, and we're going to label it with C. We also know that station B simultaneously at the same time detects the same plane on a bearing of 323 degrees. So now let's work with station B. To measure the bearing, we start with the north vector, this one, and now we have rotate clockwise 323 degrees. I'm going to add a few lines here to help me count. Now that is 90, that's 180, that's 270. I have to keep going, right? I need 323, so I have 270, so that's what, 53 degrees more. So let's say up to here. That is 323 degrees. And where I stopped, I'm going to place the vector indicating the direction in which station B detected that same plane. Well, where those two vectors intersect, that's where the plane will be, because they detected that plane at the same time. That's where I have to place point C. Okay, and finally the question, find the distance from B to C. Now it makes sense what I need to find. I need to find the segment here, distance from B to C. I'm going to denote it by X. I can see that by doing all the steps, we formed a triangle here. So I'm going to erase some extra pieces. Now let's see what we can say about this triangle. We know that those north vectors form 90-degree angle with the horizontal line or the east-west line. Based on this knowledge, we should be able to find angle CAB, this one over here. So measure of angle CAB is simply 90 degrees minus 53 degrees. That is 37 degrees. Now, can I find angle CBA, this angle here? Well, we know that this full rotation was 323 degrees, and if we subtract just this portion, we will be left with angle CBA. But what is that green portion? That green portion is 3 quadrants, right? That's 270 degrees. So in other words, measure of angle CBA is 323 degrees minus 270 degrees. That is 53 degrees. So we have triangle where we know two angles. But notice the following. If we add those two together, 37 degrees plus 53 degrees, we're going to get 90. So together, angle A, I'm going to call it this way, and angle B equal 90 degrees. What does this tell us about angle C? Well, it has to be 90, right? So it has to be the right angle, so that all three of them add up to 180. And that is the great news, because we're looking at the right triangle, and we already have, quite a lot of experience for finding unknown sides in the right triangle. In this right triangle, side AB, which is 8.6 kilometers, is the hypotenuse. And then side X, well, it can be either adjacent or opposite side, depending on which angle we choose, and it doesn't matter which one we choose. We're going to get the same answer in both cases. So let's say we choose angle that measures 37 degrees, angle A. And for that angle, X is the opposite side. So since we have the opposite side, we have the hypotenuse, we have to use the sine function. So sine of 37-degree angle equals the opposite side, which is X, over the hypotenuse, which is 8.6. Now from here, if I multiply by 8.6 on the right and on the left, I'll find that X equals 8.6 times sine of 37 degrees. That I'm going to enter in the calculator. 8.6 times sine of 37 degrees. And we got this value. In the problem, it doesn't say how to round, but since the east-west line was given to us as a decimal rounded to the nearest tenth, we're going to round the length of the segment BC same way. So let's round to the nearest tenth, so 1 decimal place. Now, the first digit is 1, but the next one is 7, so we have to round up. It's going to be 5.2. So X equals approximately 5.2, and that's in kilometers. So the answer is, the distance from B to C is 5.2 kilometers. Now, as you can see, the computational part is pretty easy, right? So once you have the sketch done and figure out that you're looking at the right triangle, well, it's just like one-step problem. But setting the sketch is the more challenging part of this problem, but it's very, very important and crucial part. So you really want to spend time on setting up the correct sketch.